Okay, in this section, the last couple of topics that we'll cover are the force vibration solution and the concept of impedance, concept of power absorption by systems. So if we look at the force vibrations, of simple harmonic motion, a simple oscillator. This is the mechanical resistor, stiffness, mass. Now I'll use X as the displacement. So this is a damped simple oscillator. And its equation of motion can be written in time domain as such, or I can write it in terms of complex values. Okay. Now, before we go, I just want to draw your attention to a couple of things. When you look at these terms, I know mechanical engineers probably know, and electrical engineers also in different terms. This is an inertial force. Mass times acceleration is just inertial force. And here is what we call a mechanical dissipation, but it's proportional to velocity. So the faster it is, the larger this force is. And this is the spring constant proportional only to displacement. Okay, each one of them is a force term, so that right-hand side is also a force equation. So when we start solving this, I'm going to solve it without regard to the complex tildes. And the solution for this would be why is that? Because it's a forced vibration problem. Technically, it has two solutions, transient solution and a steady state solution. Transient solution is the one that's associated with its natural frequencies, but because there is damping in the system, it disappears. So in a very short time. So over the long time, it will be just the steady state vibrations which must follow the force frequencies. So we do assume the solution to be of a form that follows the frequency of the forcing function for a linear system. And in fact, if you substitute this, I should have A here, okay? The equation becomes the following. So, and the amplitude then is, of course we can get rid of these. Sorry, could you erase this X? It should be A. Okay. And the amplitude of this is F over So the solution, one can put it back into the original F over this would be the solution of the system. Okay. Let's examine this just very simply, okay? Just very quickly. Usually, it's good to have some estimation of the extreme cases. So let's look at very, very small, at very low frequencies. What happens? At very low frequencies, what happens is definitely this is gone, and this can be ignored. Okay, so what you have then is, okay, and what is that? That's the static displacement. Okay, when you hang it, okay, that's where essentially it is. It's almost like a zero frequency case. Okay, well, that's interesting. What happens at very high frequencies? At very high frequencies, what can you ignore and what can you not ignore? Yes? Any answers?
The effect of mass.
Say again?
The effect of mass.
The effect of mass. Okay. At high frequency means this number is going to be much larger than both of these. Okay? So you have essentially an inertial effect. See, inertial effect, and this would be a stiffness. We'll touch this later on, okay? But from an acoustics point of view, think about sound going from one room. We're hearing other people in the other room now. Okay, sound waves are coming through, let's say, the wall. And what that means is the wall is actually vibrating at those frequencies, but not at all frequencies because we cannot hear them clearly. We can hear something, but not everything. Okay? So, when we say at low frequencies, it's a stiffness effect, whereas at high frequencies, it's a mass effect. This has relevance into oscillations, how one should actually influence, something's not right here, how one should influence the sound transmission problems. And finally, when we talk about the relevance, I mean the high-low, there's one other thing that's left, okay? That's resonance. And what happens at resonance? At resonance, this component becomes zero. Right? Everybody buys that? And then what we're left is the damping. This is something isn't... Oh, yes, I know what it is. Okay, sorry. Coming this down, it's RM, R mechanical, okay? All right, let's go back. I should give this lecture all over again. Okay, now we go. Yeah, that's okay. I knew something wasn't quite right. I couldn't quite see it. Sorry. Okay, so at resonance, when this is 0, what you're left with is the damping effect. Okay? Damping is the important factor. Now, we want to use the same expression to define impedance. Okay? Impedance for mechanical systems is force divided by the velocity that of the system that it drives. Okay? We will come back later on to acoustic impedance, where it will be pressure over the velocity, particle velocity of that particular system. But right now, the mechanical. And what we want to do is go back here and rewrite this equation in terms of velocity. So if I take this equation just for a moment, I'm rewriting it correctly. Okay, so this one we can say I omega times mx dot. And this one is k x dot divided by I omega. Okay, so what am I missing here again? Let me just not doing this rightly. Just a moment. Let me just erase this. All right. Okay. This is velocity. So the impedance expression is okay. This is what we would call the resistance. And this is the portion that's reactance. and we can write it as Rx. Okay. This is an impedance expression. That's a complex expression. Now, a few things to notice after you write. A few things to notice. Once again, at resonance, okay, at resonance, this term is equal to 0, and impedance is purely resistive, meaning all the energy just goes out. You will also note that if you have just a mass, okay, that you're pushing, it resists the motion. This is inertial impedance. So when you have just a mass that you're pushing through, okay, or you're oscillating somehow without any springs or losses, this would be the impedance of just a mass. It's called the inertial impedance. And so you can see each one of these are the impedance effects. And in electrical engineering, there are similar types of impedance expressions for electrical systems. Now, in terms of impedance, we can write displacement, we can write power displacement, for example. See different terminology. Okay. Okay. So displacement in terms of impedance. The actual impedance, this is a complex quantity. The measured impedance or measured displacement is the real part. So we say X is the real part of X. And from here, you can see, let me write it first and then we can discuss it. Sine omega t minus These are mechanical things. But one thing I'd like to just draw your attention here is if you look at I here and when you expand it, their multiplication, the real part of which also using that, real part of that gives a sign. Okay, that's where it comes from. The final topic of this portion is the power relations. The instantaneous power supplied to a system in watts, for example, in general is found by as a product of the force and the velocity that it causes. So the power, we say, is, and in our case, if we are exciting the system, F cosine omega t, and the system responds with a time delay. Okay, remember velocity can be expressed in terms of impedance. Not only displacement, but velocity can be expressed in terms of impedance. Then what we have here is f squared divided by impedance and cosine omega t times cosine omega t minus phi. Okay, this is the instantaneous power. In practice, what we're interested in is the average power. And the average power can be obtained from these expressions by integrating the instantaneous power over a period. Okay, so we take this expression, integrate it over a period, and that should end up with an integral of cosine omega t cosine omega t minus phi dt, and which finally should give us f squared to cm cosine phi, where cosine phi is the ratio of the resistive to the total mechanical impedance. Oh. And if we substitute that, as soon as you write this, I'd like to go over this because there's an important topic here. Okay. We express the instantaneous power at a given time t as a product of the force and the velocity that it causes in a system. We're now considering the simple harmonic system, but this is true for all physical engineering systems. And force is an amplitude times its harmonic oscillation, and the velocity response is written again in terms of force and impedance, and we have this expression. But the average power, which is much more important from an engineering point of view, is its integral. And we substitute everything, and we get a result. And let's take a quick look at this result. What does it really tell us? We have as power force amplitude squared, impedance squared, and resistance or dissipation. Okay? Now, how much power you can give into a system is dependent on the losses that it suffers. Okay? And so if the system does not have any losses, it will not accept power. That's what it says. That's all it is. See, otherwise, in fact, if you look at here, if you do not have this part, it's reactance. What reactance means is energy you put in, it comes back. Okay? Force excites, it comes back. Excites, it comes back. That's the reactive field, back and forth. Energy goes back and forth. But the minute you have a loss for a steady state, energy pumped in is equal to the amount that's lost. So the power equality comes in there. So power input into a system is very much dependent on the mechanical losses that are in that system. Okay. We'll get some examples, and demonstrate some of these things in the next classes. And I will assign you a few problems also. One last thing that I want to do was do a cavity resonator. Well, there are a couple of things I'd like to do, but well, and the cavity resonator is very similar to the tube experiment that we did a minute ago. By the way, do you have any questions about these impedance, power? It's all clear. You have seen these before? No? No. Yes? Maybe. Yes. You in other forms? Okay. Well, that's very good then. Okay. So what we have tried to do today then is cover a number of different things. We talked about use of complex amplitudes. We talked about oscillations, how to express different frequency summations, energy of vibrations, impedance, forced vibration responses, etc. Just to conclude it with some sort of acoustics is an example relates to the Helmholtz resonator. Helmholtz was a very, of course, well-known physicist, physiologist, a doctor, okay, baron. So the scientists of the Middle Ages were scientists in many different senses of the word. So Helmholtz was one of them, and he has discovered a number of different things, and this is one of the things that's attributed to it. Helmholtz resonator. Okay. And sometimes we call it the acoustic cavity. For example, when you're driving in a car and you open one of the windows, you start at a particular depth of the window, you start feeling this boom, boom, boom sound in the car. Okay, that's Helmholtz resonator. Okay, it just resonates the volume. Similar with the Coke bottles when it whistles as you blow over the top of the bottle. So the way to model it is pretty simple. We just take some sort of a volume over which there's a neck. Okay, neck part is the important part, and neck has a length L and an area A. And the density of gas is rho. So here the mass is rho A times L. Mass of the neck area. Okay, mass rho A L. Okay. The compression is adiabatic. So, not PV, but PV to the gamma is constant. And as you remember from last time, just a couple of minutes ago, same approach. So small change in volume produces a small change in pressure. Okay, so that's the relationship with small changes in pressure related to small changes in volume. So for a small oscillation, then the volume change can be written as, okay, this is the oscillation. I want to color this a little bit, but yeah. Oscillates. Then the pressure is gamma. And the restoring force on the mass of air in the neck. Area times the pressure fluctuation, which gives us gamma A square P divided by the volume. Okay. So from here, the equation of motion of mass in the neck rho A L Okay, and so we can see that this is the mass and this is the stiffness. And we can write this as a harmonic equation, and omega squared should be the ratio of these two. This is square root of the speed of sound. So the oscillation frequency is proportional to the speed of sound divided by okay. You write it down and let me just go over it. Okay. Okay, what we're doing is, I want to give you a very quick review of just this part of what we have done, just so you see how natural frequencies, oscillations, simple harmonic motion, and the gas law are all involved, okay? A volume, an arbitrary volume, its shape, doesn't matter. And it has a neck, like a bottle, a tube, okay? And if you can, by blowing on it, okay, or by some other means, you start an oscillation. Let's say air is coming through here, wind, it sets an oscillation. What we want to find out is the acoustic response of this cavity resonator, because I'll explain what these are used for in a moment. So we start with the gas law, as simple as that, okay? And then, as we have done before, we are able to express the relationship of change in pressure to change in volume. That should be straightforward also. And we say, fine. When we talk about oscillation, we're considering the mass here as it moves up and down. A small motion of that, with the area shows how much this volume changes. Okay? Volume change. Well, if we start substituting the volume change slowly into where that is, well, if the pressure is changing, okay, in the volume itself, then the force that's acting on it is its cross-sectional area times the change in pressure. That's fine. Well, the mass itself is density times A times L, and its acceleration. And the restoring force we have already just found. Then what we do have is stiffness divided the coefficients. When you divide them, it gives you the natural frequency of the system. But what is interesting here that you probably did not know before is the ratio of the specific heats multiplied by pressure divided by density is equal to the square of the speed of sound. Okay? So in this system, the cavity resonant frequency is determined by speed of sound and essentially the geometry of the system. Okay? So if you have different gas, helium, for example, you're going to have a very different resonant frequency. Or if you're at very high altitudes, temperature is different, speed of sound will be somewhat different, so you have a different natural frequency. Now, what do you use these for? Helmholtz resonators are used in a number of different applications. They could be used as sound absorbers in theaters, in automobiles, what's called an induction noise. in an automobile. They actually put a long volume the shape is determined by how much space is available in the engine, because you don't have much space in the engine. So it can just actually be a very funny shape. It doesn't matter as much, okay? And it acts like a Helmholtz resonator. Helmholtz resonators are, and we will follow this later, when you have a duct and sound is propagating, you want to avoid it from going down and coming in and disturbing, for example. You can put a Helmholtz resonator here. So the reaction here will actually prevent sound from going down the tube. So applications like that. So it's good to know this. I think that's all I'm going to say today. This was a bit of a rough start, but I think it will be a lot more smooth from next lecture on. Thank you. All right.